Vector components. So sometimes you're asked to find the x and y variables or components for a resultant. So in our first example, it says, find the x and y components of the vector 15 meters per second at 65 degrees north of west. So I've drawn a scale diagram, and you don't actually have to measure it out, but you do want it to truly represent your problem. 65 degrees north of west, so start at west and take 65 degrees towards the north, and then there's my resultant of length 15. We need to find the x and y components, and I tend to use the sine and cosine function, and my sine is my opposite over my hypotenuse. So I've plugged in my 65 degrees, my interior angle. I have y as my opposite, and 15 is my hypotenuse. Solve for y, and it's 15 times the sine of 65. Once you have a value, I put in my units and check for sig figs, which is 3, and give it a direction. So my y is 13.6 meters per second, and it points in the north direction. Your arrows always need to point towards your resultant. For the x component, I have the cosine of 65 equals x over 15. Cosine is adjacent over hypotenuse. So x is adjacent to your angle of 65. I solve for x by multiplying 15 times the cosine of 65 degrees. My value is 6.34. I add the units, meters per second, and I verify the direction as west. In our second example, find the x and y components of the vector 35 meters per second at 20 degrees east of north. So 20 degrees east of north. Start at north and go 20 degrees. Again, draw a good representation or an exact scale drawing. I want to find my y and my x components. This time my sine is my x component. So my sine of 20 degrees, my opposite side is x over the hypotenuse of 35. Solve for x, 35 times the sine of 20 degrees. Your value of x is 12. Again, it's 3 sig figs. With units, it's 12.0 meters per second. And that vector is heading east towards the resultant tip. My y component is adjacent to my angle. So I have cosine of 20 is equal to y over 35. Solve for y, 35 times the cosine of 20, and you have a value of 32.9 meters per second, and that vector points towards the north. Notice both arrows are pointing towards the resultant. Our third example, we have an airplane, and it's traveling at 605 kilometers per hour, 30 degrees west of south. So south, and then 30 degrees west, and my resultant represents 605 kilometers per hour. We're finding the x and y components. So my sine is opposite, so it's x over my hypotenuse, 605 kilometers per hour. So sine of 30 degrees equals x over 605. X is equal to 605 times the sine of 30. Your value for x is 303 kilometers per hour, and the direction is west. You're pointing towards the resultant. For my y component, it's adjacent to my angle, so I'm using my cosine function, and my cosine of 30 is equal to y over 605. Multiply 605 times the cosine of 30 degrees. Your magnitude of y is 524 kilometers per hour. The direction is south, because if I point south and then I point west, I'll get to my resultant. This problem has a second part. It asks how far west and how far south has the plane traveled in 2 hours. So we have solved for the x and y components, and I've called them the velocity west and the velocity south. We're traveling at that velocity for 2 hours, and the problem asks, what's my displacement to the west? So I'm going to take my velocity to the west times the time interval. So 303 kilometers per hour times 2 hours. Units cancel. To the proper sig figs, you have 606 kilometers. And it is a vector, so we could say west. On your south velocity, you have 524 kilometers per hour. Time period, I put a seconds there, that should be hours. Your displacement to the south is your velocity times time. So 524 kilometers per hour times 2 hours gives you 1,048 kilometers. To 3 sig figs, you round to 1050 kilometers, and it is a vector, so you should have a direction, and this one is to the south.